So we are recording. So just like yesterday, where we still did the same type of stoichiometry, mass to moles, using the appropriate equation, mole ratio. In yesterday's, we had two numbers for the reactants, so we had to determine which one to use. We determined how much we need. We determined how much we had or have. And ultimately, we determine which is the limiting reagent, and we do the problem from there. So this add-on is a little bit different. Now we're interested in product. All right, so yesterday's was all about reactants, given two reactants. Today it's all about the products, or a product anyway. And kind of a measurement of how well we did an experiment, how well we actually did it. And that's why at the very bottom, or near the bottom of our lab, that's due Saturday, there's one question where it says calculate the percent yield for the equation that you chose it. And that's kind of a measurement, how close you were to getting what you predicted from stoichiometry. So if you've already started to think about the lab, you might know what I'm talking about. If you've done the prediction and you find the two are really close, what you actually got from the test tube versus what you got theoretically from your calculation, well, the percent yield is a percentage. How close did you get? Were you 80% close to getting what you expected? Or did it not work so well? Were you only 50% close? And we calculate it like any other percentage. What did you actually get divided by what you should have got if you did it perfectly times 100. Just like any test you do. You do the same thing. What did you actually get? What could have you got if you did it perfect? Divide times by 100. So today's calculation is really nothing. It's just calculating a percentage. All right, so let's define what we mean by yield. And I was speaking as if you knew the term yield. It's just simply how much product you obtain. Because we're a country school, and we got to listen to Taylor Swift in the morning. And you all know what yield is, right? Because you hear your parents and your grandpas kicking the dirt, talking about how great the corn yield was. I guess it's the same idea. You can't be mad at me for making fun of farmers. I grew up on a farm. I'm allowed to do that. I'm also allowed to make fun of amputees. Just a little bit, though. But you can't make fun of me. I better stop talking. Yep. It's when I get a microphone on and I get it recording. I feel like I'm on a stage. Okay, so the theoretical yield, that would be what we predict to get if it was done perfectly. That would be like the perfect mark on the test. And we use stoichiometry to get it. So as you are going through the lab, you'll notice it says calculate the theoretical yield. Use stoichiometry. It is a calculated value. My next slide says actual yield, or sometimes called experimental yield. And it's what we would get actually from an experiment. And then our calculation percent yield is as easy as calculating any percentage that you get on a test. All right, actual yield, whoops, back up. So does the amount of product that is actually obtained and measured at the end of an experiment, which we did, and therefore we have an actual yield, in that you actually did an experiment. In the questions that we're going to do here that involve calculating percent yield, I have to just tell you what the actual yield is. So you're not actually doing an experiment, but we're just building it into the question so you can practice it. So how do you know the actual yield from a question? It'll often use the term actually obtained, or was obtained in an experiment, or the mass of the product that was produced. Now, it won't always say from an experiment, but it's almost implied, all right? So we have to give you that, as opposed to, well, what you did on Wednesday, where we did an experiment and we actually got a mass of the product. So percent yield is a simple calculation. I'm not a fan of the term efficiency, but I guess it does apply here. I'll talk about what we really mean by efficiency. There's two parts to this efficiency of a reaction. And actually, if I relate it to fuel efficiency, I guess the term efficiency is applicable. So that's my classic, division. Actually, what did you actually get over what you theoretically could have got if you did it perfect times 100? Just like anything that you do when you get a test back, you calculate a percentage. Same thing. So what does it mean by efficiency of a chemical procedure? Yeah, and again, like I said, if we were to use a fuel economy of a car, efficiency might be something to talk about. A car burns octane, and that's the same reaction that we did in our little example yesterday for our stoichiometry quiz. And I'm not going to balance it up, but actually, what was it? It was 2, 25, 8, 16, and 9, I think. Okay. All right. So what do we mean by a measurement of efficiency? I suppose if you had a car that wasn't tuned properly, maybe the air filter was plugged and the engine didn't get enough oxygen, then you wouldn't get the reaction to be complete, right? The other product here is energy. There's a lot of energy given off. That's what makes the car go. So if you didn't have enough oxygen, then you wouldn't get all the energy out of it, and it would be a decrease in efficiency, and we could calculate that as a percentage, okay? So I guess that's a way of thinking of it. Was it 100% efficient? Now, even talking about that car scenario, what then would prevent a reaction from being inefficient? Well, if you had a plugged air filter and it wouldn't let the air into the car, then that would be an equipment error, right? So errors can cause inefficiency in a reaction. And that's what my next slide is. What types of things can decrease the percent yield? Now, there's another factor that can also decrease the percent yield, which I can't use this as an example. I guess I could. If you didn't have enough oxygen, there's a secondary reaction that could take place. If you don't have enough oxygen in a combustion reaction, what kind of products can you also get? Any ideas? What other products do you get if you're trying to burn something and you don't have enough oxygen? What other products do you get in place of carbon dioxide and water if it's not? You get carbon monoxide. And you could also get solid carbon. That's the soot that we saw in that first lab when we were testing the Bunsen burner, and that was a yellow flame. So you can also have secondary reactions, other reactions that take place. That can also decrease efficiency. I remember in university, we had an organic chemistry lab, and I was not good at organic chemistry. I got out of it. Organic chemistry is the study of carbon and reactions that it undergoes. I guess this could be an example of one. And we were to make a chemical called styrene. And styrene is a precursor chemical to make something called polystyrene, which is styrofoam, all right? So we had to make styrene out of the raw products. And we were told in the lab that if you could get 55% yield, you did a fabulous job. And it's not because of inefficiencies and errors, but it's because of secondary reactions. Styrene is a big molecule. So when you mix those reactants together, there are many other types of molecules that can be formed other than just the styrene. And so the most efficient method that we were using would get you 55%. So secondary reactions can also decrease that. Now in our lab, we just decompose sodium bicarbonate. So it's not a complex reaction. There's not a lot of secondary reactions. There isn't any secondary reactions that take place for that one. But in this case, there was. I think I ended up with like 25% yield. And at that point, well, not that point, but after that year, I thought, organic chemistry is not for me. So then I went on to do a lot of mathematical stuff, calculation chemistry. So what then could prevent a 100% efficiency? So really what I'm giving you here is possible errors. These are errors that could take place other than side reactions. I guess side reaction could be an error, but it's something that you can't control. I suppose errors are uncontrollable. So I guess a side reaction is still an error, a possible error. So I'm sure some of you have already started to think about your error analysis. But if you haven't, I'm giving you some good examples. So that first one there, reactants aren't pure. So even in our lab, especially in our lab, we started with some sodium bicarbonate, also known as baking soda. Well, when I order chemicals for the science department, I go through a particular chemical supply company, and I can buy sodium bicarbonate from them. But because it's coming from a chemical supply company and it's got a really fancy container, they charge, large amounts of money for baking soda. So I don't buy that. I go to the grocery store and buy some baking soda and dump it in my container every time it gets low. Now, when you order chemicals, you can buy what are called reagent grade versus lab grade. And the reagent grade is always more expensive because it's more pure. The lab grade is really more for demonstrations and things like that. And then there's grocery store grade, which is what I use. And I have no idea what the purity of that is. So if it's not pure and you're weighing that on your scale, assuming that that's 100%, there's going to be other chemicals in there. Not necessarily toxic ones, because we're talking about food grade sodium bicarbonate. But there could be some sodium oxide in there, or there could be some sodium chloride in there. Sodium is a very common positive ion, especially in food grade stuff, because it's not toxic to us. So, well, it raises blood pressure, but it won't kill you. So there could be other sodium compounds in there. So that's a thing. Product is lost due to transfer from another flask. We didn't experience that in this lab. Again, we can talk about, yep. Yep.
If there's stuff left on the bottom, could that be like a possible...
No, you mean like in the bottom of the box or something?
No, like if there's like, if you're putting new stuff on top of stuff, old stuff, like not expired, but...
Could it expire? So, in terms of the sodium bicarbonate itself, well, we learned that if you heat it, it decomposes, and it breaks down into, well, whatever you determine it to be out of those four reactions. So I've never done a study or looked anything up. What temperature does it need to start decomposing, right? So are like hot summer temperatures of, say, if it gets to, say, 30 degrees in that chemical storage room, because they don't want to turn the air conditioning on in the summer or who knows what, is that enough to start a decomposition? It could be. That's an interesting idea. I don't know that, but I don't see why not. So that could be already impurities because we've started to decompose it. Yep. That's a good question. Again, would compression, you're now just asking me to kind of hypothesize on that, which is okay. That's my job. Would compression affect something like sodium bicarbonate? Can you decompose it by physical squishing? You know what I mean? Well, we already saw nitrogen triiodide. Remember the nitrogen triiodide? Well, if I touched that, it decomposed, right? So we know that decomposition can happen due to mechanical squishing of some sort. That precipitated the chemical reaction. We would have to do more studies to see whether sodium bicarbonate does a very slow decomposition if you were to like hit it with a hammer. Like, I don't know, that's an interesting experiment. Could it easily be done? Sure it could. I could ask you to take a bunch and hit it with a hammer and then do the exact experiment that we did this time and see if we get the same results. It would be interesting to see. I don't know that. That's a good hypothesis. Okay. Product loss due to transfer. We didn't have too much issue with that. It's typically when we talk about aqueous solutions. All right, so if I have something dissolved in this beaker and I want to put it in the Erlenmeyer flask, you guys all know that when you're dealing with liquids, you can never get it all out of there, right? So if I had a reactant in there, I would have some stuck, right? Again, it's kind of like making cookies. If you've ever made cookies, which I don't think I ever have, but I've watched people make cookies, when you go to take the batter out, you can never get all of the batter out of the bowl. Does that make sense? You know what I mean? So even though you're trying to get 100% of your ingredients to become cookies, you never can. Same thing with chemicals. Product loss due to filtration. We didn't filter anything, but we often do. If we form a precipitate, right, we can take a filter paper. The folding I was doing there kind of gives it like a coffee filter orientation. We use a funnel along with something like an Erlenmeyer flask, and we filter it. And if you're not careful, you can get some of it to go over the side. So if you're not careful, you can lose some of that product. It ends up in the bottom instead of in the filter paper. Some filter paper, well, no, all filter paper have a particular grade in terms of how big the holes are. We can't see the holes, but there are holes there, obviously. So some holes are bigger and some particles can get through. So you can lose product that way. Product not dry or reaction incomplete. We could have an incomplete reaction in our experiment. Usually when you filter, the stuff that you catch is all wet, so you got to put it in an oven, carefully not too hot, to dry it out, to get all the water off of it. But even though you think you've got it all, you end up sometimes with some water in there, and so you've actually got too much, okay? If it's a decomposition like ours, and it doesn't completely decompose, this can result, right? This can result in greater than 100%, right? Because if it doesn't all decompose, it's still way too heavy. You see what I mean? And therefore, you can have a top number, your actual yield, be too big. If it's like a synthesis reaction where it's getting heavier, then it wouldn't be 100%. It would be less because it wouldn't be heavy enough, right? A product loss due to splattering. Very often, we want to sometimes get substance that are dissolved in a liquid. So let's say we had some salt in here, some sodium chloride, and we wanted this out. We would put it in an evaporating dish and we would evaporate it away. And as you get close to the end of the process, the little bit of water that's left tends to boil and it splatters. Again, there's a food example just like it. Cooking bacon on a frying pan, right? When you start to cook the bacon, there's lots of water in there, and then the water evaporates and the grease comes out. And when you're near the end of cooking the bacon, the grease, the fat, the oil is on top, the water is underneath. And when there's only a little bit of water left, it boils very rapidly. It forms a bubble and it goes, you know what I mean? It gets you. It burns you. And you lose some of the oil. So if you could imagine that the purpose of cooking your bacon was to preserve as much of the bacon grease for some reason, in the end you're going to lose some of the bacon grease onto the top of the stove because splattering is going to eject it from your container. Similar things happen here. And I've already mentioned side reactions, okay? So again, many of these things could be used for error analysis in the lab that we just did. All right. At this point, I'm going to do 3 examples. This first example is just the percentage calculation. The second example is stoichiometry, then the percentage calculation. And just because it's so much fun, the third example, well, I won't tell you. I won't tell you the surprise in the third example. I won't wreck the fun for you. This one does not need a balanced chemical equation. This is simply me demonstrating the percentage calculation. You probably can already build the percentage without me or without my help. You sucked the whole fun out of that question. You did it in 2 seconds. Good job. Not even worth writing the question down, eh? It's right, what you've done there. There's nothing wrong with it. It's just, I'm going to write a nice equation. I'm going to make it look all pretty. And you did it like poof. So you can see here in the terminology, we're kind of guiding you towards 2.52 grams of the precipitate was actually obtained. If the theoretical yield was 3.01, determine the percent yield. So very straightforward. I don't need to see this equation, but because I'm the teacher and I'm teaching you, I'm going to write it down this first time, and then after that, you don't need to write it down. But percent yield is the actual yield divided by the theoretical yield times 100 2.52 grams was actually obtained, 2.52 grams. 3.01 was theoretically able to be obtained. That's the theoretical yield that would have been obtained by stoichiometry. Times 100. Kaylee, what do you got? 83. Give me a decimal. 0.7%. Ooh, we're off to a roaring start here on Friday's lesson. We just did a percentage. All right. Good. Now let's review some stoichiometry and then stick a percentage on the end of it. Oh, and by the way, I have posted the solutions for the test that I just gave back. The reason why I remember to tell you is because this exact reaction was the reaction you studied in the very last question on the test. And when you did the empirical formula, you get Hg2O. And by the way, when you reverse the crossover, that means it's mercury 1 oxide. Where many people write mercury 2 oxide because they see the little number 2 beside the Hg. How can I help you? You can. There you go. Yeah, if you need periodic table, come on up. I've got some. Okay, so let's say I'm just throwing a question asked you on the test, which is what's going to happen. And you have no idea what you're dealing with. You don't know whether it's a theoretical yield. Well, you know what? It is a percent yield problem because it says, what's the percent yield? But if you weren't even paying attention to that, you were setting up your stoichiometry the way I've been trying to teach you, write down the information underneath the particular chemical in the balanced chemical equation. So it says 250 grams of mercury 1 oxide. There it is, 250 grams. And after it was heated, 195.3 grams of Hg was obtained. 195.3 grams. All right? Now, yesterday I said to you, well, if you have two numbers in this position, it's a limiting reagent problem, and you've got to deal with it like a limiting reagent problem. Now, these two numbers, there's also two numbers here, but this isn't a limiting reagent problem. How is this different than what we did yesterday? What made the limiting reagent problem, and what makes this a percentage yield problem? What is different about it? So, limiting reagent, we're given the reactant numbers, right? When it's a percent yield scenario, we will be given at least one reactant and the product. So what I like to do here is I like to say this is the actual yield. I put that beside it because it says that's what was obtained, which means I need question mark grams theoretical yield. So when I'm told the product number, and I'm told two numbers, then that's the actual yield, and I got to find it. Now I go through my stoichiometry the exact same way that I've been doing all the way along, and then I stick a percentage at the end. So I'm hoping at this stage of the week, you are able to proceed with the 3 steps, and I catch up to you. Oh my goodness, 417.2. We want N. I need the triangle without me walking across the room. Molar mass is grams per mole. So that's M over MM, right? So that's 250 over 417.2. Do we have a number? What do you got? 59. Have you got another digit or two? 0.5 something something? Anybody got a few more digits? 992. That's lots of digits, but that's okay. 992. I'm okay with that. You could have had 0.600. Would have been okay too. And now we're moving on to the next step here. 0.5992 over 2 equals x over 4. So we're getting bigger by 2, right? The 4 goes up there. 4 divided by 2 is 2. That multiplied by 2, 1.200, essentially. No? I'm trying to do it in my head, but maybe I shouldn't. That could be 1.19841. Yeah, it doesn't matter whether you carry all those extra digits. I'm okay with 20, right? 1.20, right, to 3 decimals. You could carry the 119. It doesn't matter. Moles, that's right there. 1.20. I need an Hg by itself. That's a 200.6. Mass is equal to molar mass times moles. 200.6 times 1.20. I can't do that. Have you got that number? No? What do we got? Did I move too fast? I wanted you guys to be ahead of me. What do you get? 2, 4, what'd you say? 240.72. That's plenty of digits, grams. So we're comparing it to 250, so really 241 would do, right? Grams. So there's our theoretical yield. Now we just do our percent. Percent yield. Oh, I hate the word yield. It's got one of those IE things in it. Percent yield is, what did we get? Actual, 195.3, theoretical, 241, times 100. Caleb, you looking at a number? 81. You got a decimal on it? 0.0? 81.0? 81.0%. All right? Not too tough? And one more. One more just to make sure. And it's good practice. Yes, it does. Yeah. Did you just predict that because of my how predictably evil I am, or did you look at the two numbers and say, "Hold on, there's a lot of numbers in there"? Yeah, it is. Oh, and it's because I'm evil as well. And it's good practice. Review of yesterday. Typically, a percent yield on the end of a problem, stoichiometry problem, I usually just add 2 marks, right? So it's like put it in the equation and get the answer. So the ultimate of like heavy hitting super mark questions would be a limiting reagent problem with then the percent yield on the back end. That could be like worth 15 marks. Just because you give little things for all those little things. Yep, you gotta go right. Molar mass is correct. Good. Yep, all that stuff. Balanced chemical equation. I'm hoping this is an easy one. Some sodium is reacting with chlorine. Synthesis reaction. Should be able to come up with a product. Are you going to tell me a reaction? We'll wait for everyone else to catch up. Yes, it's the product. That is incorrect. Check your charges. Sodium, Na. Doesn't have a number with it. No, not because it has a charge of +1. Remember, I got to get you guys the way of thinking that all elements other than our diatomic ones are just by themselves. So Na is by itself. Chlorine is Cl. It's one of the diatomic molecules, too. Now that they're together, you then use the charges to cross over. I think we've got a +1 and a -1. Na +1, Cl -1, 1 and 1, which means I think I need a 2 and a 2. In this case, it looks like we have absolutely every number. I'm going to have to do a limiting reagent problem to see which one is less on the have and need. I will then use that to get my theoretical yield, and then I'll put the percentage on it. 19.5 of the product is isolated. Actual yield, question mark, theoretical yield. And now I do a whole lot of arrows and calculating and stuff. Go ahead, do stuff. And again, I will catch up. Oh my goodness, the tape is broken on my foot. I go through a lot. Coolest thing about a fake leg and using tape like that, it's like I'm getting ready for hockey every day. Oh, that tape's failing again. I can feel it. It's coming off. Struggling. Don't be distracted. Chemistry. You guys have much more room working down your page, right? I would likely go like that calculation there, mole ratio there, and I'd likely do the need calculation there, and then I would put the other ones down below. But because I'm trying to squeeze this on this for the video, I'll do a mole ratio in there. I'll do that other calculation out there, and I might do the other one down there. That's just me doing some screen management. 23.0, Na, 23.0. I got to find moles. N is, and again, if I don't see it, I'm going to make a mistake, just like you guys. So I write it down every time. Molar mass is grams over moles. So moles is mass over molar mass. 0.0. That's a 0. So again, my calculator's got that number right there. All I got to do is a quick calculation. I keep those numbers in my calculator. That's 35.5 times 2, so that's 71.0. I have 0.197. I need 0.180. I have more than I need. So it brings me back to sodium as being the limiting reagent. But if it doesn't ask you for the limiting reagent, you don't have to worry about that. The trick to this at this point is, it doesn't matter whether I use this number here, the 361, or this number. I can just choose the low number and go that way. The low number is the limiting. The technical definition of a limiting reagent or reactant is which reactant is limiting. That's the definition. But in between these two numbers, the small one is the one that's going to limit it. So I could do a mole ratio. I'll do it down here. The mole ratio of 0.180 over 1 back up to 2, x over 2. So that's getting bigger, twice as big, so I'm doubling that. Bring in the 2 up there. And there's that. 0.28 times 2, 0.360 moles. 0.360 moles. And now I need an NaCl molar mass. 35.5, 23, 58. That's a terrible 5. 58.5 grams per mole. Mass, molar mass times moles. There it is there. Still in my calculator. .1 grams NaCl. That's my theoretical yield. Oh, and I'm really getting squishy. I forgot I had to do one more calculation. Right there. Lots of room. Percent yield, I'm just going to go percent Y, is actual 19.5 divided by theoretical 21.1 times 100. 100 goes on the end there. So 19.5 divided by, I could use my answer button here, but I'll go 21.1 equals times 100. I actually don't times it by 100. I can just move it over. 92.4%. 92.4%. Do we have agreeers? Do we like it? Question?
Why did you do that down there?
This is this mole ratio right here. I apologize. So this mole ratio right here, to go from there to there, is the Cl1. So this mole ratio is that guy there. So you know how we do it? In this, the limiting reagent is always the smaller one. The 0.18 is smaller than 0.19, isn't it?
Yeah, but I was saying it's like the reverse what we already had up there.
Well, but that's a true statement, but that has nothing to do with anything. The only reason it's reversed is because this is a 2 down to 1 ratio, right? And now I'm going 1 back up to 2 ratio. That's the only reason it looks like it's reversed. It's not, I'm not going backwards. I'm going to this one. But you're right. The reason it looks the same is because it's 1 back up to 2. But it's a different mole ratio. But it looks the same. Yeah. Yep. Okay. That's that. There's a worksheet just like the other day, just like yesterday, with some percent yield questions on it. And on the worksheet, there's also some textbook stuff. I've already posted the Chapter 5 review. I think I did, or did I? Maybe I didn't. I posted the review questions. Yeah. Anyway, there they are again, if you haven't written them down. So again, this weekend, practice. Then come on Monday, question. Practice. Then Tuesday, correct. ACE test, high fives everywhere, feeling good. That's the way it's going to go. The other 2 slides to finish things off. Yep. As soon as everybody gets set. Yep. I'm going to stop reacting before I say something stupid again, like I have in the last couple of videos.